Hello, have decided to produce my second screencast on experimental design and how it features in VCE exam questions. This has been prompted by some of the questions that have come up in the SAC written question sections that relate to the practical sections. The particular questions that I was thinking of were on the aspects of the experiment that were controlled and those which were variables. The first question we need to ask ourselves is, why do scientists bother actually performing experiments in the first place? The main reason is to extend their knowledge beyond what it is that they are observing. It's to arrive at an understanding of what they're seeing and working out what factors or features of the environment in which that experiment is being performed are actually having the effect on the inputs into the experiment itself. This has been done really for many thousands of years. The picture that I have here is of Galileo, and one of his most important experiments was his work on the laws of motion. He really busted some of the beliefs that had been created by Aristotle some 1,000 years before, when he decided that objects moved in a way that related to the various minerals or ingredients of which they were made. Galileo instead related them to the environment and all the other forces that act upon them. Now, the requirements of an experiment really begins with an observation. Let's get my little pointer here. We have our observation here. Now, the observation would generally be something that we have seen in our environment and has really created a problem, or at least a question. Once the scientist has that, they are then able to define that problem. Now, defining that problem is really just a matter of working out what they don't understand about that problem, and working out, that can then lead to the hypothesis. The hypothesis is really framing a question that identifies what they already do and don't know, and what they are going to do to increase their knowledge of whatever it is that's creating that original observation. To begin with, they need to gather evidence, which is really to collate everything that they already know, and decide whether or not that is going to help them to understand the original problem. This will then enable them to design an experiment which can test the hypothesis. The testing of the hypothesis is really the experiment itself. And when gathering the evidence and proposing the hypothesis, what the scientist is doing is really narrowing down the criteria that they're going to be focusing upon. And I'll get to this in more detail later. Now, when that hypothesis has been tested, we will either have a rejection or a retention of the hypothesis. Really, the rejection is going to be a negative result generally, and a retention of the hypothesis is more a confirmation of their beliefs. Once they've done that, they are then able to develop their theory a little bit further. They have, whether the result is negative or positive, they now have more information to work upon. This can then be fed right the way back up here into another observation, which they can then use to not just define their problem, but refine the problem and go on to produce an even better hypothesis with more evidence, and then a more targeted hypothesis again. So they can then target or test a more targeted hypothesis, which improves the experiment the second time around.
Farting noise in the bathroom.
Alright, the fundamental point to remember when dealing with hypothesis is that you need to identify the criteria being studied. This enables the scientist to narrow down exactly what they're going to be looking at. They need to determine exactly which criteria and aspects they're going to be studying and how it affects particular things. For a good experiment to work, that needs to be really as narrow as possible so that the information can be targeted. Once they've worked out what they are going to study, they need to then identify the variables against which they're going to be comparing everything. Now, variables are going to be the things that are altered in the experiment. For instance, an experiment might be working within a range of temperatures. It might be performed at different temperatures. It might be performed at different pHs or atmospheric pressures or concentrations. But whatever it is, those variables must be worked out beforehand and must be put into the hypothesis. The other thing that a hypothesis needs to do is, or at least very early on in the experiment, a benchmark must be provided. Now, the benchmark is really, it creates a point from which everything else can be compared. Or it's usually done with almost an ideal set of circumstances, and this then creates almost a starting point for any comparisons. Alright, just to revisit it, the variables are the aspects that are changed to study the effect. Now this can include a whole, really the entire spectrum of things that might be studied. It could include temperature, it could include pH, it could include time itself, it could include volumes, excuse my writing, it could include concentrations. Really, all of these things can be varied when doing a range of experiments. We'll go into that in a moment in the next slide. Now, the most important thing is that only one of these things is done at a time. If you're going to be looking at how temperature affects the rate of a reaction, then that will be the only thing that you vary. If you're wanting to look at how concentration affects the rate of a reaction, or the amount of reactants or products that are produced, then concentration will be the only thing that you vary. You do them one at a time. You must stick to the KISS principle. Varying more than one variable at a time can give you very messy results, and it can lead to uncertainty as to exactly which variable it was that was having the given outcome, or even whether there is some sort of complex interplay between the two variables. Let's take, for instance, two completely fictitious substances. One of them is naphthalic acid, which was invented in Nathalia today, and we add that to unobtainium, which is the substance that's being mined in the film Avatar. Now, with any acid metal reaction, the product is always going to be hydrogen gas and a salt. In this case the salt would be unobtainium naphthalate, which is just as awkward and fictitious as either of those two original reactants. But let's say, for instance, that we are going to be combining these two and looking at how the concentration of naphthalic acid affects the rate of reaction. What we would be doing would be using various test tubes. Let's say we're taking 3 test tubes here, and we're going to have a certain amount of solution in each one. But in this first one we're going to be using a 1 molar solution. In the second one we're using a 2 molar solution, and in this last one here, this gentleman's in the way, we're using a 3 molar solution. And in each case we give ourselves a small amount of unobtainium that we then add to the solution. 1 in each of those. Now in each case we're going to end up with hydrogen bubbles coming off, being given off as a gas in each and every case. Now we are going to have to collect that gas using a bung and a pipe that goes to a different container in which we collect the gas. This isn't quite how a chemist would do it, but it's close enough. And our gas ends up in here, our hydrogen gas there. Now, if by some sort of scientific magic we are able to measure how much gas we have in here, we would then be able to give ourselves a rate of reaction. We could work out how much gas we're getting produced every minute. This then gives us enough information to be able to look at the amount of hydrogen produced, which is relative to the rate of the reaction, relative to the amount of naphthalic acid, or the concentration of the naphthalic acid. Because you remember we're starting out with a 1 molar, 2 molar and 3 molar solution. If you don't do chemistry, you probably won't have come across these particular definitions before. But molarity is a way of chemists telling others how much active ingredient is dissolved in a litre of water. So it's a measure of the concentration, and it's a direct measure. If you're using the same amount of solution, it gives you a direct idea of how much naphthalic acid you're working with. Now, in each case, we would be able to collect the gas, and that would then enable us to graph the amount of information that we have, or certainly the results that we have, and come up with some sort of relationship. The most important thing is coming up with the relationship between the concentration and the rate of reaction. Now it's very important, I'll get to this later on as well, that the rate of reaction is not confused with the amount of gas that's produced overall. What we're looking for is how fast that gas is being produced. That is the rate. You could almost describe it as millilitres of hydrogen gas per minute, almost. You could give yourself a rate like that. Once we have that, we are then able to decide whether or not we have enough information to refine our hypothesis and take it a step further. Now, if you remember that experiment that we just performed with the naphthalic acid and the unobtainium, the thing that we were varying was the concentration. The things that we are keeping constant was pretty much everything else. As much as humanly possible, we were keeping everything else constant and only altering the concentration. The things that stay constant are called controls. Those are the things that we are controlling. We are not controlling the concentration. We are varying the concentration. There is there's almost a double entendre, a double meaning here for the word control. Control in this case means to keep something the same. It doesn't mean whatever it is that we are that is under our direct control, that we are able to deliberately alter. That is not what controlled means in this case. It means we've made a conscious decision to keep it the same. The other thing that can be a control would be a variable free run, as I've said here. The option to have a control in an experiment is usually where you are combining all of the reagents apart from the thing that you are varying, apart from your variable. In this case, you could imagine that we have our test tube here and we have our little piece of unobtainium. That could almost be a control. We could then collect any gas that comes off of this in our other container and see how much we're receiving, and seeing whether or not we're getting any H2 being produced in here. Are we getting any? Now, we also have to remember that we're not using pure naphthalic acid. Acids work when they've been dissolved in water. So logically and reasonably, you would also add water. We would have an H2O here, and we would have our unobtainium there. Putting that in water enables us to see whether or not it is purely the thing that we were varying, which is the naphthalic acid concentration, that was producing the result. If by some chance we combined unobtainium and water and still got hydrogen coming off, then we know that the naphthalic acid is not the only factor that's causing that. And that then means that we need to go back to the drawing board and really rewrite the entire experiment and see what we can combine it with, or at least be able to subtract the amount of hydrogen that's being produced by the water. If by any chance we don't get any water being produced, let's see if I can subtract that. So we can get rid of our water here, or we get rid of the hydrogen that's being produced by the water. We can now say that no, we're not getting any hydrogen being produced by that at all. So we know that there is no reaction happening, and we can say that this is a control as well. This would be really the benchmark against which we can measure the performance of the acid and metal reaction, knowing that we get nothing from basically all of the other reagents put together. Okay, so just to revisit this again, we have our 1, 2, 3 test tubes with our little bits of naphthalic and unobtainium here with our naphthalic acid. The only thing we have varied is the molarity. So we have 1 molar, 2 molar and 3 molar solutions. We'll have all of these bunged and have all of the water, all of the gases being collected elsewhere. Now if we look at this, the only thing that we have varied is the concentrations. Everything else has been controlled. We have exactly the same quantities. We have the same amount of solution. We have the same amount of unobtainium. We can even be really uptight about the whole thing and use exactly the same sort of test tubes and bungs. We can use the same sort of glassware. We can make sure that the unobtainium that we've been using has all come from the same batch. It's possible that we got them from two separate jars. One could be much older than the others. So to try and keep as many things exactly the same as humanly possible, this is what gives us our controls. These are the things that we are controlling. We are not controlling the concentrations. We are varying the concentrations. That is the difference. And when dealing with this sort of thing in science, you need to be quite clear that we are not using a more classical English definition of the word control. Now, some other exam questions that have come up have been looking at the ways that information is being graphed. If we were to look at our unobtainium, we would have a vertical and a horizontal axis. Now, almost always the vertical axis is the thing which is being studied. The horizontal axis is the thing against which it's being measured. In this case, it would be time, because we're looking at the rate of reaction, and rates are always a factor of time. The thing that is being measured would be the rate of the reaction, which would be the volume of hydrogen being produced per minute. We need to be very clear when looking at this that we're not looking at the amount of hydrogen that's being produced as an absolute, but we're looking at the rate of that hydrogen production. In this case, let's just say, for instance, that we were taking the 2 molar solution and not messing up the graph by adding 3 different lines. We would start off with a reaction that probably begins quite quickly, and then as the acid and the unobtainium get used up, it would peak, and then the reaction would come back down again, like so. This means that at this point here, the reaction has come to a stop, because our volume of hydrogen being produced per minute on our vertical scale, this line here represents 0. So at 0, our starting time, which really should be starting from there, if we go up to a peak here, which is our peak production rate, which is when the reaction's really going full tilt, and then from then on it's all downhill as we get less and less molecules of naphthalic acid and unobtainium floating around in that solution. They're finding it harder to find each other and react, and then eventually there are none left at all, and our reaction comes to a grinding halt. The big difference that we have with this, let's just erase this now. The big difference that we would see if we were comparing this with the absolute quantity of hydrogen being produced is really the entire shape of the graph. We would be seeing instead, we would have our vertical axis here and horizontal here. The horizontal one would still be time, and our vertical axis axis rather than being the amount of hydrogen being produced per minute, would simply be the volume of hydrogen produced. Both of these would start at 0. Now, without the volume of hydrogen being produced, we would have a very fast reaction initially, where the hydrogen in the jar, if you remember, we have our test tube like so, that's then leading into another gas jar here with graduations on the side that somehow we're able to measure the amount of hydrogen in here. That's going into there like that. The amount of hydrogen in this jar, we would see that level rising, and then gradually it would level off. Now, once it's completely horizontal here, then we know from about this point onwards our reaction has come to a stop, because it's now constant. There is no change. That point would tally very nicely if I go back to our other colour, and we have our hydrogen per minute. If we compare this with the rate of reaction, we would have our rate of reaction would peak and then come back down again. This point here coincides with this point here. This is a quite a complex mathematical principle. It does involve calculus, but really you just need to be very, very aware of whether you're looking at the volume of hydrogen being produced, or whether you're looking at the volume of hydrogen being produced per minute. So you're looking at either the absolute production, or you're looking at the rate of production. And that is one of the things that has come up in the SACs that has caught people out. You need to watch that very carefully. Right, now I hope everybody has improved their understanding of this a little bit. If not, you can either contact me on the Edmodo page, or send me an email on this email address here. slattery.paul.p@edumail.gov.au. I have to excuse my writing, my stylus is a little blunt. I hope that's helped, and if you have any more questions, just let me know in class.